We're delighted to have Dr. Nancy Love with us today, University of Michigan. She's the JoAnn Silverstein Distinguished University Professor, as you can read here on the slide, and the Borchardt and Glysson Collegiate Professor of Civil and Environmental Engineering at the University of Michigan. She works on the interface of water infrastructure, environmental quality, and public health in both domestic and global settings. Her research is focused on understanding how engineering, design, and operation of water systems influence sustainability and equitable access to healthy water services and advancing methods to achieve a circular nutrient economy. She has held leadership positions in multiple organizations, including the Water Environment Federation, International Water Association, and the Association of Environmental Engineering and Science Professors. And she is a fellow of all these three organizations. She's a licensed professional engineer in the state of Michigan and a board-certified environmental engineer. So we're delighted, as I said, to have her here. Give her please a warm round of applause, and I'm happy to hand over to Nancy.
Thank you, Roy. Let me move it forward here. Oop. Okay. Well, good. Oh, wow. There we go. We're getting the lights adjusted here. Thank you so much. Thanks, Roy. And thanks for everyone for being here and for the opportunity to come to Waterloo. I've been to Canada several times. This is my first time to Waterloo. My grandfather came to the United States via Nova Scotia from Scotland through Canada. So I've had a lot of family trips up here and visits to other institutions, but I'm really happy to be here with you today. A lot of people think of the work I've done historically kind of on the wastewater side, but my work is really at the interface of water and chemicals, microorganisms and chemicals, pardon me, in water systems. And really increasingly over the last couple decades, I came out of my practice experience where I worked in consulting before I went back for my PhD, doing almost all drinking water work. This is really focused on the drinking water side, but there are some connections I'll bring together at the end. And it's a storyline of experiences that my students and I have had in a couple of different locations that I'll call resource limited, places where we don't have tremendous investment, and the impacts that those places have had that then result in issues with water quality and therefore public health. On the left side of the screen, you see a picture from Flint, Michigan, and I will use that as a scenario. I've spent many years and continue to be associated with Flint. And on the right, you see an image I took from a very western hotel in the city center of Addis, which has a very much integrated between kind of your new development and your traditional kind of housing, slum housing, or the Ethiopians prefer to call it slum housing as opposed to informal settlements. And I'd like to acknowledge some of the work was in collaboration with a number of people I will point out at the end. So I'm going to really just jump right in, and I'm going to talk about storage and how excessive storage happens and why it's important to know about storage and the impact that storage can have on water quality. So I'm going to start by talking about Ethiopia and the work in Addis Ababa. And so to orient everybody, I've got a map of the continent of Africa. Ethiopia is on the Horn of Africa, and Addis is kind of towards the center of it. It's the major city. Addis Ababa and Dir Dawa are the two kind of major governmentally independent cities in the country. And on the left, you see the city center of Addis is really the top part here. This bottom here is kind of parts where you've had migration into the city. This is an area that is not as developed formally, if you will, but the major city part is in here. It is showing you over time from the 1990s to 2010 to where we are as of 2019 and even more so. The growth of the city has been immense. And I'll show you what that means from the standpoint of their water system. So the spaghetti kind of thing you see in the middle there are streets and water lines that move through the city. And there are two surface water treatment systems and groundwater systems. So the surface water systems are Gafirsa up here in the northwest. It's the original and smallest of their water systems. It's a traditional coagulation, flocculation, sedimentation. And then you have the Legadati system over here, which is larger. And down here is the Akaki well field. And the Akaki well field is where a lot of the growth is happening in terms of water supply. I've done a little bit of math for you over here on the left. You see that the total supply as of around now 2024, 2025 in Addis is about 677,000 cubic meters per day. The demand, now the population of Addis is around 6 million people at this point in time. The 2025 demand is about half. I'm sorry, the supply is about half of the demand at this point in time. And you've seen this growth here in the Akaki well field in terms of trying to support the growth for that demand. And the future plans continue to be associated with the well field. In terms of their system and what that means in terms of the percentage of the population, Ethiopia is the second largest country in Africa. It's about now 125 million people. When I started working there, it was about 100 million people. And started working in 2011. About 80% of the population lives in slum housing. 7% of people who live in Addis are on a sewer connection. They recently upgraded their wastewater treatment system right around the beginning of the pandemic. And after they upgraded it, 7% of the population is on sewer system, so it didn't change access, it changed the quality of the treatment. Even though the system is bigger, the system before, I won't talk about today, but I can with anybody who wants to afterwards. So you have kind of some of the traditional, a lot of people who don't have plumbing inside of their residences, access to sanitation services are outside of the residence, et cetera. So this is your typical, I would say, kind of rapidly expanding city in a very resource-limited space. Ethiopia is one of the poorest countries and continues to be one of the poorest countries in the world. So what does this look like? That light's a little hard to see this, but when I fly in, this is a picture I took from my airplane. That used to be a farmland. There's rapid expansion of high-rise apartments as people are coming in from the rural spaces, and some of the like informal housing is being dismantled and moving people to these kind of high-rise spaces. Mostly on the outskirts of the city, and then you're busing people in and out for jobs and so forth. In this picture on the right, I'm standing at the water, the Awasa, which is their the Addis Ababa water and sanitation offices. And these are on the south down by the Akaki well field, new high-rises here that they were in the process of building. Still, even though you have these vertical structures, people are still hauling water because the water pressure or you don't have a pumped system to move the water to the upper levels. So it is still storage through in that way. Where am I going here? Why did that do that? I don't know why that's in there twice. So what does storage look like? Storage in a rapidly expanding city. Pretty much everybody has a storage unit of some kind. Whether you have plumbed water or not, and often plumbed water may be, if you're lucky, a standpipe outside of your home, but usually it's a neighborhood standpipe. And you're storing water because of the intermittency of the water as well as the inadequacy of the water supply relative to the demand. You're getting water access maybe 2 to 3 times a week in the city. And so people will have informal agreements. You see a lot of water tanks on roofs and things like that. There's some storage in the distribution system, and there is some in-house filtering happening, at least on the campus where I worked. So now we're going to shift, and I'm going to talk a little bit about the United States, where I live, and kind of lay out that scenario, and I'm going to, again, use a case study. So let's talk about funding for water systems and how we got to where we are in the US with our infrastructure. So on the y-axis, I have percent of federal contribution to building infrastructure. And on the x-axis is going to be time starting in 1977. And I think this goes out to 2014. I don't remember. There we go. Yeah. So this is how the US government has proportioned the percentage of demand for infrastructure expenses that are paid for by the federal government. The lines across the top, the blue and green lines, those are transportation, aviation, et cetera. The red line is water. And so in the 70s, right after the Safe Drinking Water Act and the Clean Water Act, there was an immense investment in infrastructure. There was also an immense investment in infrastructure back after World War II, so back in the late 40s, early 50s. And for those of you who think about design life of water infrastructure, those 2 points, there's a design life associated with what was invested then, and we are at or past that design life for that massive investment. The historical kind of philosophy is that water is a regional or a local responsibility, and so it is a regional or a local responsibility from the standpoint of continued investment. So we're at about 7 to 10% is the federal contribution. So even with the most recent Infrastructure Investment Act that came out where there was money put out for investing in upgrading our infrastructure, water still got only about 10%. So that's been a constant in kind of the federal investment since the early 80s. And you can look at kind of what that means in terms of the dollars per capita for different types of investment. At the same time, there's a lot of population shift happening in the United States. And so the lighter colors here, the yellow, are the slower growing parts of the country where population growth is either slowing or stagnating or decreasing. And the darker black parts are where the population is expanding. And you can see kind of it just shown here in terms of different decades and how the South and the West is where people are moving. You also know that the South and West is where we have wildfires and where we have no water, or much more limited water. And so people are moving to where water isn't. And we'll see how that goes. I'm not sure if I'm too far away. Okay. And so the other thing is the consumer price index and looking at how people spend money on water and different kinds of utilities. So this shows you, this is from JoAnn at Michigan State. She's one of the people who really collects data on this, and so I don't have her updated information, but I think it's very similar in terms of all the different kinds of utility services you might pay for. The thick line here is water and sewer. Sewer is usually combined in the US to your water use. They monitor the water use and then they tap on a percentage of it for sewer. And you can kind of look from the same time period here at this line, and you can look at that line, and you can get the point. The point is that water, the cost of water, is something that the local community bears. And it comes out in the form of water rates. And if you are in one of those communities that were lighter in color, where you have shrinking population, loss of investment, loss of industry, loss of jobs, it's not clear where that money is coming from, because now you have less money to put into paying for that infrastructure upgrade. And what is the first thing to go? The first thing to go and avoid is maintenance costs. And so this is what has been happening in the shrinking population cities of the United States. And one of those cities is Flint. So this is a picture of, and I've been working in Flint since the crisis, about 2015, and I currently serve on the Water System Advisory Council, which is a city council appointed position, and I serve as a technical advisor where they need that kind of technical support. This is what's called Chevy Commons. This is where the Chevy used to be built in Flint. This is the notorious Flint River. This is the Chevy Commons after that factory went away and all the jobs that came with it. And so on the bottom you see is just a Google map of a neighborhood, and there are large sectors of the city of Flint that look like this, where normally you would see, you know, a dozen or a couple dozen houses around a block. And now you see one or two. And so if you zoom down to the street level, the one on the bottom right is what it looks like. Now you have a street, and our water lines and our sewer lines are under the street, right? And you built these back in the 40s and 50s, and maybe a little early in some parts of Flint. And so those lines were designed for growth, because everything on our class is let's design for growth. Well, this isn't growth, this is stagnation, and this is loss of population. The population of Flint's about half what it was designed for in terms of the water system. So you still have a line that needs to have water in it that assumes growth, and you have one house right there pulling off it. That one's obviously not doing it. This one is off. These have been raised. Those houses are not there. So when you have a loss of population, you still have to push water in the water line, keep pressure. You have a higher period of time that water spends in the pipe, and that's called water age. So your water age goes up. And so water storage increases are associated with water age, which affects water quality. And so in the US case, Sorry, let me go. I'm not sure why this is. Yeah, I'm just not getting close enough to this. This is now a map of Flint that was created in partnership with the city by my colleagues at Wayne State. And it is showing you the water age across the city of Flint. The water treatment plant sits up here. And for the city of Flint, it doesn't treat the water. It receives it from Detroit, which is 70 miles away, through a big pipe. For a little bit of time, it tried to treat it. We all know what happened then. But what you see is in the lighter colors and then the dark pink and white colors, those are really super high water ages. We typically want maybe 48 to 72 hours from treatment plant to tap. And you can see these hours of water age in some parts of the city and down in here where we're beyond that time period. And the Chevy Commons, that big plant was right here at the corner. You still have the big lines that were serving that plant that no longer needs the water. And so you have parts of Flint that have water ages in the order of weeks in certain neighborhoods and certain areas. And so what do we know about storage and water age and water quality? We know and have known for a long time. These go back to 1992, the AWWA reports, 2002 US EPA reports, and even recently. We know that there are chemical, biological, and physical issues associated with water age and storage. The bolded words are those that have a direct impact on public health, and then the secondary ones are secondary but can lead to public health issues. So I'll talk about some of these, but you can, disinfection byproduct formation, obviously, corrosion control effectiveness, nitrification product degradation, microbial regrowth, etc. So let's go back to that map of Flint now. And what I've put on here now are the chlorine residual monitoring locations. These are selected not because they're the best place to monitor chlorine. They're selected because they are the best place they perceive to monitor disinfection byproducts. And you'll notice that they're pretty much almost all, except for this one here, at the extremes of the city because they're looking at a street map. And they're assuming that, like, if you go to the extremes of the city, that must be the furthest point. Hydraulically, it's not. You need to look at a water age map to figure these out. But anyway, you'll notice where the points are generally not. They're not in this worst area, other than that one right there. And this one here is actually sitting over a pink spot, so a really high water age area. So let's look at what happened during the water crisis in terms of chlorine residual in the city of Flint at these locations. Free chlorine time, and the typical chlorine here level, it varies seasonally, that's known. We know that you're going to have more demand of the chlorine in the summer, and you're going to have higher levels in the winter when the demand's lower and its dissolution is higher. Here's the crisis. Very unstable, went on to the, it was trying to treat it itself. Oops, sorry, let me go back here. This down here is that M6. And the time periods here, these are these are extended periods of time of no residual. Okay, so you can imagine what's happening biologically, not just about lead, but biologically. People were exposed to lead, for sure, but people died of pneumonia. And that's the part of the story that I think often gets missed. Since then, and I don't have an update on what it is, but I can tell you when I go in Flint, the chlorine residual is pretty high in a lot of places now. They really put some supplemental across the city, and you see that it started to go back up. So this is what I think created microbial instability in large sections of that system for a year and a half. Microbial instability that resulted in some of the things I'll show you. One of the things that we looked at and became aware of when we were thinking about the pneumonia-causing agents that were, we were understanding that there were more pneumonia deaths and illnesses in the city, is that if you look at what Legionella, which is a pneumonia-causing waterborne agent, Pseudomonas aeruginosa, some of the others, what they prefer to grow on, it's not sugars. They can grow on sugars, but that's not their preferred substrate. Their preferred substrate are amino acids. Think of a pneumonia organism. It's going to attach to your lung. And what is your lung? But a big muscle. And so they have proteases. They're breaking down the protein, and they love amino acids. So we were looking at the protein fingerprint of Flint's water at low and high water age to see if, in fact, the water chemistry changes as well as you have cycling and biogeochemical cycling happening inside the pipes. And so using fluorescent EMS with a collaborator at, sorry, I think some of the names, I lost them here, sorry. It was with Dave Holbrook at NIST, our federal lab, looking at increases here in what we would call proteinaceous kind of content in the water in the high water age. And we also see in the high water age, we see a reduction in the molecular weight size. And then we actually do go out and we've measured non-quantitatively amino acids, and you can see certain amino acids that are present in high water age that are not present in low water age. So there's a pattern here associated with organic chemistry, nitrogenous organic chemistry changes with high water age that we are continuing to work on, just getting our methods down, because working on nitrogen and organic carbon at these low levels takes a little bit of work. So the idea is that you're changing as your water age increases the nature of the organic carbon, which changes the substrate options, which can change the competitiveness of your pneumonia-causing agents relative to the background microflora. So I think we need to be aware that DOC transforms into opportunistic pathogen substrates. And that has not been the conventional wisdom. The conventional wisdom is that they're there because there's a lack of chlorine residual or there's an increase in iron, but not looking at changes in organic carbon. I think we need to be paying attention to that. If you look at the US and Legionnaire's disease outbreak, this has just been on the increase. I suspect Canada is experiencing something similar. I don't know how much of this is due to monitoring, et cetera, but we certainly would expect that some of this has to do with aged and old plumbing, because Legionella loves iron and loves stagnation, loves storage. So in our study, we looked at the incidence of Legionnaire's disease in the Flint crisis, and were asked by the state to determine whether or not the Legionnaire's disease outbreak was associated with the water change. And our evidence suggests that it certainly was distributed across the city, not just at one hospital. And so that would provide evidence that, in fact, it did have an impact. And I can talk more about that for anybody who wants to. There was an independent separate study done by epidemiologists at Emory University down in Atlanta, who took data, historical data of 7 cities like Flint, compared it to Flint in terms of the typical mortality rate associated with Legionella over long periods of time. Here's the, so the dotted line here is the Flint case. And you see that it's actually aligned with its comparison cities until you get to the crisis. And when you get to the crisis, there's a big shift from the comparison cities to Flint, suggesting that there was something different in Flint at that time from what would normally be expected. And they indicated, while the state still maintains there were only 12 deaths from Legionella or Legionnaire's disease, that statistically at least 70 more deaths. There were a lot of people who died of pneumonia where there was no antigen test done to confirm whether it was Legionnaire's disease or not. So we'll never know. But their statistics suggest that it could have been. Again, storage in the system. So we've had papers in 2019 right before, or right sort of after with the federal government. These are people from the EPA acknowledging deterioration distribution systems affect public health. And you can also see a CDC paper that also looked at data talking about the incidence of microbial disease and the cost it has, not only in public health, but just the cost to people. And so some kind of shocking statistics based just on the data that's available on waterborne outbreaks. So it's no surprise then that when Gallup surveys Americans, which they do all the time, that their confidence or their percent expressing a great deal of worry when it comes to environmental things that they're surveyed, the top one for decades has been drinking water quality. And you see that this would be 72% greatly worried back in 2000. And 2021, it dropped to 56%. So it is more than half worry. So therefore, Americans filter their water a lot. We've got filters on our faucets, we've got filters under our sinks, we've got filters in pitchers, and we're buying bottled water. People don't trust their water, even though in most cases that water is really of great high quality. And so The Flint crisis certainly, I think, amplified some of this. There are racial and socioeconomic differences in trust. So if you look at the percentage of Black and people of color who don't trust their water versus those who are white, it's quite starkly different. And you also look at poor versus higher income people. So we have, it's a socio-economic and a demographic factor as well, a lot of things that come with that. And then if you look at what people turn to then when they don't trust water, and you look at it across racial lines, tap water choices, so this would be white is in the first bar, who drink tap water versus bottled water versus sugared sweetened drinks. And you look at the impact and kind of looking at how the Hispanic and non-Hispanic Black are the two middle ones, are moving to bottled water, purchased bottled water, and purchased sugar-sweetened drinks. These are not necessarily healthier choices, but it's linked to this lack of trust and lack of transparency, or sense of lack of transparency. So this is, I think, a big factor when you have created a system that has kind of the outcomes that we're seeing. So actual or perceived poor water quality motivates bottled water use and point of use water management. What does that look like? So my group has spent quite a bit of time, 5 years before the Flint crisis, we were already working on point of use filters and looking at the microbial stability, or how a point of use filter changes the microbiome you're exposed to between what the tap water and the utility gave you and what your point of use filter created for you. And so we've disassembled these systems, we take them apart, we've looked at the microbiomes, we've done scrapes up the annulus of the filter. You can call it a colonoscopy for the filter, or whatever you want to do. And this is a clean fabric around the outside of a filter, and this is the fabric after normal 100-gallon use. So there's a huge biofilm that forms in this, and of course there's biofilm in the media itself. And so this is happening not only your point of use filter, the one under your sink, the little bottle filler here that has a filter inside. And again, much of this is probably okay, but I always flush my water when I use my bottle filter first. I give it a good 15 seconds if I'm the first one there, and then I go for the water because I think it is of high quality. But you do change the microbiome across that filter. So depending upon your water system, depending upon the nature of the chemistry of your water system, you will have different microbiome shifts. In Ann Arbor, we are chloraminated, so we have ammonia in our water. We have a higher nitrogen base, which means we have nitrification that occurs in our system. And we see, for instance, this is a relative abundance using 16S analysis of water going in. I'm going to point you to the bolded area here. These are ammonia oxidizing bacteria, the percentage of the population. This is the fabric, and this is the water going out. And if we take that percentage and we use a quantitative approach then to kind of come back and look at the actual numbers of cells, you see an increase in nitrifiers coming out. So you have nitrification happening across these filters, and in some cases producing nitrite. We didn't do the nitrite analysis, others have, like in Washington, D.C., and you can see that happening in these filters. In these cases, we actually saw an increase in mycobacterium as well across this filter, which is the pathogen of concern on our chloraminated system. And it went up about at least 2 orders of magnitude in some of the filters. So it's changing what you're exposed to. And we have to maintain these filters in order to mitigate and reduce the impact that might have. Done a lot of work on flushing and what happens and so forth, so I'm happy to discuss that more. But then Flint happened, and we had been working on these filters for 5 years, and they suddenly deployed 20,000 of the exact same filters we had been studying, not for lead. We were looking at them for what I was just telling you about, but now they were being deployed to remove lead, and they remove lead very well. Since then, I've been working in Flint Community Schools. We've monitored almost 176 hydration stations with activated carbon block filters in it. We do not see lead breakthrough. We see a lot of lead coming into them. It's not lead service lines, it is lead in the building. It is plumbing in the building, up to 600 parts per billion. And actually a good like 70% of the filters have more than 15 parts per billion coming onto them, but they remove it. But then the microbial stability is another question. So during the crisis, when they had were just switched back to Detroit water, but there was that period I showed you where the chlorine residual was all over the place, that's when we were monitoring in the city. This is very complicated, but the bottom line is this is the same city. This is kind of a higher level census tract kind of map of water age, where you have your higher water age down here. We took volunteers for this study. We didn't really have a funded grant. It was done in a manner that was tagged onto another project where there was a grant for people who wanted to be part of the study too. Then we would replace their filter, and then we would take the filter, we would interrogate it, and then we'd go back 2 to 3 weeks later and take that filter again and interrogate it. So we have good data on what happens over a controlled period of time microbially on these filters. And what you're seeing here is for one particular family of bacteria, the Enterobacteriaceae, and we point that out because there was a Shigella outbreak that happened around this time. And Shigella are in the Enterobacteriaceae, and we did see Shigella DNA fingerprints, but below our quantification level, but we saw amplicons from it. And people were, one of our collaborators from Flint was actually hospitalized for this. The ones that are kind of the orange colors, and I'm sorry for anybody whose color don't work for you, but I'll try to point them out. The triangles suggest the first sampling and the second sampling, the first filter and the second filter. And if it's white in color, it means we didn't really see a change in terms of change across the filter. If it's orange, for those who can see it, this color here that I'm pointing to, it's increasing. And if it's blue, it's decreasing. So one of the things that happens is there are a lot of variables that we weren't measuring that are influencing what's going on. But you do see that in a lot of cases in this high water age area, we wish we had more data up here, we tend to see these increases across the filter. So this is an area that I think needs more work with a well-funded, statistically designed study. We also did work with Stenotrophomonas multifida, which is a pneumonia-causing organism, more often associated with hospital-acquired pneumonia. And there were steno community-acquired pneumonia cases in Flint, and the house where one of those individuals lived lit up with steno. We had non-detects through most of the system, but we had a handful of like, I think it was like 7 houses where you see orders of magnitude increases in steno in the water. And those houses were all in high water age areas. So I'm pointing all this out because storage matters, and we need to pay attention to it, and we need to pay attention to it, the microbial, the emerging microbial opportunistic pathogens that we're not monitoring routinely, especially in vulnerable places where people, you have differences in health kind of status, and there was a lot of that in Flint. So yeah, these are just news articles showing you kind of what's happened with regard to filters in schools. And so in the United States, the state of Michigan is the first state in the country to move to something called filter first, which acknowledges the fact that when it comes to putting filters in for lead mitigation, lead is like whack-a-mole. You know, it's intermittent, you have soluble, you have particulate. It depends on how you monitor it as to whether you catch it. It's not, monitoring can spend a lot of money monitoring, but the bottom line is in these old buildings, you're gonna have lead, period. And Flint's schools are an average age of about 72 years. The US average of schools is like 45 years. They have lead. And so just filter. That's what Filter First does in the state of Michigan. Now it's required of every school and daycare. And so this just makes that point. That also means that there's kind of a burden put onto those schools in terms of this added element. So we have been monitoring, as I mentioned, in Flint schools with hydration stations that were donated. There was funding donated to install them. And through 3 different sampling campaigns, these are the lead concentrations going in, and you can see the ranges that we see over the 3 sampling campaigns. These are listed at 1 only because 1 was our method detection limit. We had non-detects in every single one except for 1, 2, 3, and those are all below 10 ppb. so coming out. So again, the filters work. And so what we've done since then is try to come up with a way to make this easier on schools and facilities managers. Right now, they're randomly, like maybe at the end of the year, we change the filter, but they don't know that for every given filter, if that's the best strategy, unless you monitor the heck out of it. So we are looking at simple, small device, conventional water quality parameters with some pressure information, with some metadata, using kind of machine learning models to predict lead breakthrough before it happens, so you can change the filter before it happens. And have a rig in the system in the lab, and with Alyssa Schubert, who's a former student of mine, who's now a postdoc at Michigan's Data Sciences Institute, is doing this, and is in the early phases, but with soluble lead is having good luck with her predictive model. Now we're moving to the particulate soluble mixture. So water storage increases water age. It's this plus limited source protection affects water quality. So let's talk about ADIS here briefly. We did a study, again, not fully funded, a bunch of little things here and there between ourselves and our Ethiopian colleagues, where we looked at different points along the water system, and then looked at a couple of communities and looked at diarrheal incidents in infants associated with waterborne pathogens, and looked at patterns associated with where do you see higher incidence of diarrheal in two-week diarrheal prevalence. And so, again, here's the city. I'm going to go quickly through this because of the timing. But it was not the largest study, but we did administer surveys to 712 households. And we then took samples of fecal matter from diapers from 46 infants who didn't have, 90 who didn't have the diarrheal two-week incident, and 46 who did, and then did pathogen identification. And looked at them relative to where they were in the water system. These were both up here, and they both were on the Gafirsis system. And so, just skipping past that, we also knew, having had done kind of a microbiome survey of the distribution system in Addis a year or two before, that oddly, the system between surface water start to all the way to tap, the blue box is what I want you to pay attention to. These are the gamma proteobacteria. Gamma proteobacteria as a percentage of abundance are usually maybe 5–10%. The gamma proteobacteria is where your opportunistic pathogens are sitting. So this was kind of frightening in terms of what we see in terms of the nature of their water. And this is a lot of words, but the bottom line was a couple things. One, chlorine residual was usually pretty high, at least above 0.5. But people use chlorine in their stored water, and that chlorine only lasts about 11 to 18 hours based on decay curves we developed. And you're not getting water but every 2 to 3 days. So you're definitely storing water for extended periods of time that do not have chlorine residual in them, and you have the potential for contamination back into the system just while you're using it. The Gafirsis system had significantly higher, I'm trying to remember, I guess we did have other locations because it had higher chance of testing positive for pathogen in their stool. Homes with water plumbing. This is the opposite of what you see in rural areas. Homes with water plumbing into the building had higher odds of diarrhea than did infants that received water from pipes in the yard that were shared pipes. Stagnation. You have plumbed water in the room, in the building, and just it costs a lot of money relative to income there. People aren't using that plumbed water. And we think that's probably due to stagnation. This is the opposite of what has been promoted in these regions where they're talking about, let's get plumbed water to people. So we have to be very careful about how we talk about it and how we implement it, because plumbed water is good if you keep the water moving. When boiling and filtering water, it reduced the odds of diarrhea, but chlorine addition did not. And that is because of what I'm about to show you. A lot of these infants that had diarrhea had signals of cryptosporidium. And gee, when we went, oh, I don't know what just happened there. When we went to the intake, let me go here and here, I hope. Yes. When we went to I'm standing here at the drinking water plant. The intake's right there. Those are cows. Where does crypto come from? Cows. No fence. And this is common. Water source protection is a problem. And they're resistant to chlorine. Okay, so you have to understand your pathogen that you're dealing with, and there's a crypto endemic in Addis, and so that's a problem. So what do we turn to? This is a Flint, I think this is a Flint picture. I'm trying to remember. One of these are Addis pictures. This is not the solution. This is our Band-Aid, but this is not what we need to be doing. In the US, $31 billion is spent on bottled water in 2018. It's estimated that $24 billion is the annual cost over the next 20 years to fix and maintain our water system. So our choices in how we're spending our money are pretty confusing, if you will. And so I'm going to close and offer some time for some questions by saying, hopefully exposing you to these experiences and making a few points. Storage matters, and we have to understand how storage manifests, what it looks like. It's not obvious. It's not sitting out there for you to just point to. You have to understand hydraulics of a system. And not every system has their hydraulic maps like I showed you. So really understanding storage and what can be done to improve the quality of stored water, or avoiding storage is really what we would prefer. I would argue that it is really time to invest in fit-for-purpose water systems. For those of you who know me on the wastewater side, all my wastewater work is now really sitting on the fit-for-purpose, kind of building scale, source separation side of the world. I do a lot of work on urine recycling. I just produced 55 gallons of 3.3, 1.1 fertilizer last weekend with my students to go on a regenerative farm. Made about 17 pounds of struvite from it. That and other volume. My point being that we spend in the US alone, we send about 900 billion gallons of potable drinkable water just to flush urine. I'll think about that. So it is a drinking water story too, because if we didn't have to treat all that water for that purpose, and we instead invested in fit for purpose where we treat for drinking that fraction, then we figure out how to protect people while having other water that doesn't need to be of that high quality. We can distribute our dollars better. I think we can invest in our systems. And now, given that our systems have design lives, what we're designing and building today will be with us at the end of the century, or towards the end of the century. So we have to have early adoption now to start moving us so that by the end of the century, we hopefully have much better systems that allow for fit for purpose. I think we need systemic changes in water policy, financing, investment, and so forth. I wrote financing twice, my apologies. I've spent a good amount of time the last couple of years actually developing policy and rules and standards on the source separation side. We've had some successes there. I haven't been as involved in the drinking water side. I know there are people who are doing this, but what we have right now doesn't work. And that really needs attention and work. And we need to really disrupt the traditional water innovation paradigm, I believe. Because as I've worked on the source separation side, and even some of the work we've done on this side, we run into so many barriers regulatorily, and from standards, and from all the non-technical stuff, and just understanding, and even disgust or impressions or perceptions that distract. We can have all the innovative technical technologies in the world that really work, but those are the things that are stopping us. And so training all of you students to be able to communicate risk communication as well as be able to work on both sides, I think is going to be really important for the future to be able to make these kinds of changes so that we don't just keep studying our failures, but we move towards our successes, move towards new successes. So there are a lot of people that I need to acknowledge. From Ethiopia, students are bolded. The University of Michigan, Wayne State, where I have strong collaborations there, and Henry Ford Hospital. In Flint, none of the work in Flint would have happened without the community members that have openly opened their arms and encouraged us to partner with them and for them to be co-authors on our work and papers and things. And at the University of Michigan and NIST. And so I think I wanted to just point out on the Flint side, if you want to learn more about, and I don't know how this works in Canada because I could not get my YouTube TV working last night when I wanted to, but PBS has PBS Frontline has an episode that's about Flint. It's called Flint's Deadly Water. It's about the Legionnaires' disease. It's not about lead. It's really worth watching if you really want to understand that side of the story. And it ends at a point when our current governor was elected. So there's a lot that's happened since then. But for those of you interested in water science, I think you'll find it very interesting. So I'll leave it back here, and I'll thank you for your attention.
Thank you very much. We got 10, 15 minutes for questions. Anyone? Why is water so lowly prioritized in the U.S.? You talked about that in the beginning, only 10% of the new infrastructure fund?
I think a lot of, it's interesting because when I talk to some people in the policy space, they feel like it's a solved problem, or they feel like it's solved. It's, and for many people who maybe have more privilege, it is. It feels like everything works. But it's really, I think even in Ann Arbor, where we have a very high tax base, we have challenges. We have lead in our schools. We have, microbial challenges there. There's some nitrate problems, and the water system is one of the most advanced, actually, in the U.S. as well. It's a pretty advanced system. We have, we deal with, 1,4-dioxane. We have a system for that. We're et cetera. So I think that there's an impression, it's out of sight, out of mind. For politicians, it's not well understood. I do think one of the things I would love to do at some point, and as I'm kind of getting at this point in my career, I talked to somebody actually within the last month about this. When people get elected, they go through, I don't know, governor's school or representative school where they learn about how the money works in government. They need to learn about their infrastructure too. And so I think people like ourselves need to really be available to help them understand what is and what is not. Because people don't understand the system, and the system's hidden and invisible. So I think that has a lot to do with it.
Thank you. Okay, give me a second. I'll get the.
Loud if that helps.
No, because it needs to be recorded on the mic.
I think he's recorded, so he wants you to.
And please introduce yourself briefly, if you don't mind.
Perfect. Thanks for the talk. I'm currently doing my degree in biology, and I also do water systems too. So seeing how much micro was in there was pretty neat too. With some of the results you showed of the Enterobacter ACA, you mentioned there was Enterobacter and Shigella. Did you mention what the source of those microbes were? Because those are usually fecal organisms and such. So was it improper wastewater, farmland?
So when that was thank you for that question. So Enterobacter ACA, that was water going into the filter, so that was distributed drinking water, treated, distributed, disinfected drinking water, and then it was water coming out of the filters as well. And then we saw increases across the filters in many cases where they were growing in the filter. In some cases they didn't increase, so there was a lot of variation in the filters. Which, yeah, the look on your face was exactly the look on our face, which was like, whoa. And if you're in a shrinking city that has raised buildings where they've taken a building down, what happens to your water line when you raise a building? You still have a line, it's still connected to a pipe. What the contractor who raises that building is supposed to do is put concrete and plug that line. There are no backflow preventers in Flint. And so we assumed that some of the contamination, because of the pressure changes that were happening and the lack of chlorine residual in large sections of the system, was that there was just environmental contamination of that distribution system. The other thing that happened is that they were changing lead service lines at the time. We had a lot of in the field kind of reporting. When Flint was built, the wastewater line was right below the drinking water line. So you have parts of that city where they were taking lines out, and you had a wastewater line that was, the second they touched it, it crumbled because it was so corroded. And so that soil is quite contaminated. And then they put a new line in and disinfected it and put it back in line. But if you have the kind of water chemistry changes I talked about, you may have a condition where those bacteria can still survive and thrive. And so that was what was going on in our head. I did a lot with going to other people. We went actually to the CDC. We talked to them about, here's our methods, here's what we did, what do you think? And honest to God, the people in the CDC coliform lab said that our methods were more advanced than what they were using, which shocked me because all we were doing was qPCR and 16S. So now they're better. They actually hired people. They actually hired environmental engineers as a result of Flint. They didn't have people who understood the system. And so there was a lot to be learned even within our public health sector about how these systems work, and that wasn't in place even as early as 10 years ago. Yeah.
Perfect, thank you.
Yeah. Yeah.
Monica.
There's people over here too.
I really enjoyed your talk. Monica Melko, I'm a professor in civil and environmental engineering. So I wanted to follow up on Tim's question and the notion of fit for purpose.
Mm-hmm.
So we're talking about a lack of capacity, a lack of education, where we really need it. And now we're talking about what I totally agree with, which is let's have water that's fit for purpose. Not everything we don't have to flush our toilets with drinking water. So what is your thinking with respect to the pathway to how we get there? Because we know it's not just about building the infrastructure, it's also about knowing how to use it and then knowing how to manage, regulate it, compliance. And so we probably don't need to throw out the multi-barrier approach. That's been reframed in many ways, but it still has all those same elements, and you had it up on your slide. But it's not just an investment in infrastructure, and so I'm curious to hear your thoughts about how we get there.
No, excellent, and I thought a lot about this. So I don't think we start in individual households. I think we start in places where we have early adopters, multi-use buildings, places where you have the capacity to demonstrate the technology and learn from it. Anything we've done innovative, we implement something and we learn from it, right? So I think, like on our source separation side, we're looking at multi-use buildings and places where we can learn. Like I've got a system, believe it, I have a urine separating system in my building at U of M. I've had it there for 8 years, and we were now processing into fertilizer. So we're doing the work in a place where we can learn from that with people. That's one thing. The other is risk communication in our discipline. I actually have a risk communication component now in my water and sanitation class and spend quite a bit of time on that because we don't train engineers in risk communication. And I learned a lot in Flint, but from the community members helped me learn how to do risk communication too by working with communities. So those aren't all the answers, but I think that's a starting point. It's absolutely one of the big problems with implementing fit for purpose are all the questions about the human side of that, yeah.
But a big part of the price tag is the distribution system. And so do we eliminate distributed water at that scale?
Maybe in some places, yes. Yeah.
And go to the point of something like a direct potable reuse?
Well, no, I think you still might have a distributed system, but you may not, you don't have to have everything to drinkable standards. They're doing some of this in Australia, I understand, and I haven't been there, but they're doing some of this and successfully in some places. So, and it's kind of the original purple pipe concept where you might have a couple pipes, or one is of a lower quality, but then we also do local reuse, perhaps a little more. I don't know what all forms of it is. I do think we need to start getting thought leaders and people from different sectors together to start mapping this out.
And I think what you're getting at is it starts to get to that flexibility that you were alluding to, which is community appropriate solutions.
Yes, and when you then have population shifts, then you're able to do something other than what we have been happening in a lot of communities where you have that. You're stuck with that really non-flexible infrastructure.
A lot of the same discussions going on in Canada.
Okay, yeah.
Thank you. Someone else? So KWR in the Netherlands has a water factory, they call it, which is, I think, similar to the initiative maybe in Australia that you mentioned. And they started a very low, like at a pilot level. The advantage there is that they are actually funded by the municipalities that have to pay for the infrastructure. So is there other examples in your case studies where, so you obviously do collaborate with Flint, for example, but are there examples that you can think of where this cross collaboration with municipalities directly on the infrastructure would help to or raise awareness, talk about the risks involved.
Yeah. On my wastewater side, I do a lot of work with municipalities, less so on the drinking water side, just because of the time I've spent in different places. But I think that we have some really innovative utilities in the U.S. I've worked with one. There's one on the East Coast that has perhaps the most innovative water reuse program. Not California, but Virginia. And so I work with that utility as well. And they have done some things where they have models of how they direct dollars into research investment by when they save money by reducing chemical use, say, as part of their process, that gets invested into research. And then that model, they've tried to make it make other utilities aware of it so that other utilities can build that kind of a support structure. Now, getting utilities then to partner together, we do have like the Water Research Foundation, and we have foundations we had different foundations, and they all kind of married each other and came together. So that is supposed to be a place where utilities do big work like that. I don't really think they've done it that way. It's been a lot of little projects. But it really takes the big utilities that have the revenue and the resources to partner with each other. So DC Water, Hampton Roads Sanitation District work together. You know, you've got Chicago Metro, I've worked with Denver, but they all tend to be independent. Sometimes getting them to find ways to collaborate, even if all the work is done at one space, I think would be a good model like what you mentioned.
Thank you. Any other questions?
Y'all are quiet.
If you want to have lunch, one more question. Here we go.
Oh, thank you.
Hi.
Okay.
We've met, but for anyone who doesn't know, I'm Dr. Emma Vossen. I'm the new Knowledge Mobilization Officer at the Water Institute. Hi. And that's fitting because my question is kind of about knowledge mobilization. I mean, something I've seen throughout my career is this, what we call like a knowledge to action gap. And, you know, researchers have the research, these things have been experimented on, but to implement something is so difficult. And part of that gap to implementation is about having a public sector that is, you know, educated and, you know, like you were saying about, they hired environmental engineers. Like sometimes that's what needs to be done. But as we've seen in the US right now, there's these massive cuts happening to public sector employees. And I'm wondering how, you know, how essentially that's affecting these water infrastructure problems, because it seems like a point where there needs to be more experts and there's going to be less experts.
I do not have an answer to that. I will say there is a lot of trauma right now, but I don't have an answer to that. What I will say something as you were talking, you know, some of the communities I work with are immensely resilient. So, and an example I was going to give as before you moved into the kind of today, what we're dealing with, like for the point of use filters, one of the things that kind of back to the earlier question here, that in terms of translating knowledge and sharing knowledge, one of the individuals here, Karma Lewis, she had me come and talk a few times about filters and how to do flushing and so forth, and she's like, you get up there and you're so passionate about these filters, will you help us train our community? They had someone from the EPA come in and they went door to door with, like, you know, a handout, and how do you install your filter, how do you flush it, how do you and I will tell you, these point of use filters, there's a knob on it to whether you're filtering the water or not. There's no indicator of filtered water or not. They're complicated. And so we went in with all these people on the community partner list and developed a curriculum and developed a train the trainer program. And Flint has a significant deaf community as well and a Hispanic community. So we developed the curriculum. We translated it also into Spanish. We demonstrated it through pilot testing, and then we handed it off and supported from behind. So they have that train the trainer program for how do you install, how do you operate, how do you flush, and your neighbors then train neighbors. And it's been used in Benton Harbor, and it's on my website, so I'd love to see it used more. But anytime there's been like a lead crisis, then that's available for so those are the kind of things we can do as institutions. But in terms of the loss of expertise, it's going to have immense impacts, and I can't even begin to tell you what that's going to look like even in a month, let alone 10 years.
Thank you.
Okay, thank you very much. Let's give Dr. Nancy Love
Okay,
another
thanks.
round of applause. Thank you very much.